Hello friends, I am going to take your second lecture regarding multiple expansion. In a first lecture, we have studied that if there is a localized charge distribution is there, that means in some volume there is a charge which is distributed non-uniformly and continuously. And then at a distance point, because of the charge distribution, you can see that there is a potential is going to be, we want to find out the potential. In this charge distribution, you can see that there is a multipole is going to be present. There is a monopole is also present. There is a dipole is present. There is a characteristic of the quadrupole is present. There is a characteristic of octupole is present. And everybody of this one, they are contributing potential at point P. Now consider that this distance point is very far away from this charge distribution. In that case, this total charge distribution can be considered as a point charge, and that is going to be Q. So what will be the Q is equal to? Total charge Q is equal to the volume integration of charge density rho d tau. That is the total charge will be there. And because of that Q, the potential which is going to be created over here is equal to 1 upon 4 pi epsilon 0 Q upon the distance r from this charge or reference point of this one charge distribution. So this is the way monopole contribute a potential at a large distance. So ordinarily we will start from here, the monopole and dipole terms. Ordinarily the multipole expansion is dominated at a large distance by monopole terms. So V monopole is equal to 1 upon 4 pi Q upon R square. So monopole contributing potential at a very large distance also, because it is decreasing as proportional to 1 upon R. What about dipole terms? Dipole is also contributing, but it is proportional to 1 upon R square. Quadrupole is also contributing, but it is proportional to 1 upon R cube. And octupole and higher terms is proportional to 1 upon R raised to 4, 1 upon R raised to 5, like that way. That means the potential contribution, because of the higher multipoles, they are dying off more rapidly compared to the monopoles. And hence, at a large distance, monopole term is only dominant term. And that is the potential we can consider it is created by the monopole. And that potential is equal to 1 upon 4 pi epsilon 0 Q upon R, where Q is equal to the volume integration of rho R d tau is the total charge of the contribution. This is just what we expect for approximate potential at a large distances from a charge. For a point charge at the origin, V monopole is exact potential, not merely a first approximator at large R. In this case, all the higher multipole vanishes, as I have discussed, right? So because even though there are multipoles are going to be present, but their contribution of the potential at a very large distance is dying off more rapidly, and that means whatever we get these equations because of the monopole, that is going to be dominant, and we can say that the potential contributed by this monopole is a exact potential, not a approximate potential at a very large distance. Now, because of the multipole expansion, the exact potential which we have studied in the last lecture was given by this expression, and it was expanded. Here you can see that more explicitly the potential at a distant point which is having a position vector r is equal to 1 upon 4 pi epsilon 0, the first term inside the bracket, 1 upon r, the volume integration of rho r dash d tau dash, plus 1 upon r square, volume integration of r dash cos alpha rho r dash d tau, plus 1 upon r cube r dash square 3 by 2 cos square alpha minus 1 half rho r dash d tau dash, plus 1 upon r raised to 4 volume integration of r dash cube pi cos cube alpha minus 3 cos alpha upon 2 rho r dash d tau dash, and that way this is a potential contributed by higher multipoles. This is equation 3.6 is important. The first term is the potential contributed by the monopole. Second term, the potential contributed by the dipole. Third term, potential contributed by the quadrupole. Fourth term, which I speak out, is a potential contributed by the octopole, and it is continued from n is equal to 0 to infinity. Now, if the total charge is going to be 0, so in that charge distribution, localized charge distribution, there may be a positive charge and negative charge is going to be present. And because of that, consider that the net charge is going to be 0. What will happen? The net charge is going to be 0. That means V monopole, which is contributing potential, is 0. So potential is not going to be contributed by monopole terms. In that case, the first term is not dominant. Here the potential contributed by this term is going to be 0. So what happens now? Because there are exist of positive and negative charge, we can say that there are so many dipoles are going to be present, and the resultant dipole which is going to be contributing potential at a large distance r. And that means this dipole term which is contributing, which is dominant of contributing potential at a large distance r, we can say that. So 1 upon r square r dash cos alpha rho r dash d tau dash, that is the term which is a dominant term will be there. So V dipole, the total charge is 0. The dominant term in the potential will be dipole, unless of course is also vanishes. So V dipole is a function of r, that is equal to 1 upon 4 pi epsilon 0 1 upon r square r dash cos alpha rho r dash d tau. Since alpha is the angle between r dash and position vector of point P, r. So r dash is the position vector of each volume elements d tau 1, d tau 2, d tau 3, and this r is the position vector of the distant point with respect to the reference point O. So this does not change directions. This is changing. So you can say that if we are taking a dot product of r dash into r caret unit vector in the direction of vector r. So what is the magnitude of this one? Magnitude of this into magnitude of this into, if there is an angle, alpha is the angle between these two vectors, then cos alpha. Magnitude of this is going to be 1. Magnitude of this r dash is going to be r dash, and angle between them is going to be alpha. So r dash cos alpha here in this term can be represented as a dot product of the two vectors. R caret is the unit vector in the direction of points where we are calculating the potential, and r dash which is a position vector of different variable volume elements d tau 1, d tau 2, d tau 3, etc., etc. Accordingly, r dash is changing as well as alpha is also changing, and the dipole moment potential can be written more successfully like this one. So this equation r dash cos alpha we substitute in terms of dot product of the two vectors. So r caret I am taking outside the integral. So 1 upon 4 pi epsilon 0 1 upon r square r caret dot volume integration of r dash vector rho r dash d tau. So this is a integral which is independent of the distant point P. It is only depending upon how the charge is distributed inside that volume. You can say that finite volume. So charge is distributed continuously and non-uniformly. That means this term in this integral depends upon the size, shape and density of the charge distribution only, and this quantity of integral which is independent of position vector r, and in that case this quantity is said to be dipole moment of given charge distribution, in which you can see here this integral which does not depend upon r is called the dipole moment of this distribution. So, which can be represented by capital P, which is also vector. Remember, bold indicates that it is a vector. So, P is equal to vector P is equal to volume integration of R dash, which is a vector, rho R dash, which is a scalar, because each volume elements d tau 1, d tau 2, the surface this volume charge density is varying, and it is a function of position vector r dash, you can say that. So, r dash root r dash d tau dash, this volume integration represents the net dipole moment of this charge distribution, and the dipole contribution to the potential simplifies to. So, this equation, the previous equation, is simplifies to V dipole at a function r is equal to 1 upon 4 pi epsilon 0. We have substituted for the integral a vector p. So, p dot unit vector r upon r square. So, this way, this is the potential contributed by this charge distribution because of the dipole term, which is dominant at a distance r. The dipole moment is determined by the geometry, size, shape and density of the charge distribution. That means if the size is larger, definitely the vector r dash is varying and it is having a more magnitude, and accordingly P is going to be changed. If shape is going to be changing, definitely the volume elements are also at a different position, and density also depends upon the density. So, dipole moment of the charge distribution can be given by this integral, and it depends upon the geometry of the charge distribution, that is size, shape and density of the charge distribution. Equation 3.98 translate in the usual way for point, line and surface charge distribution. Here we have considered that in a volume the charge is distributed continuously and non-uniformly. We can also say that charge is distributed over some surface, or charge is distributed on some line, or there can be a point charge distribution is going to be there inside some volume, which is a discrete charge distribution. Each one can have a dipole moment, can be given by this one. So, here instead of volume elements you can take a surface elements dA, and instead of volume charge density you can substitute sigma, which is a function of r dash. That means the surface charge density, and this is going to be r dash is the position vector of each surface element. Similarly, if there is a line charge distribution is going to be there, you can take a line segment dl dash, and this is a lambda, which is a function of r dash. Lambda is linear charge density, you can substitute, and that way you can find out the dipole moment of given distribution where the charge is distributed over a line. So, this you can utilize. The dipole moment of a collection of the point charge, if the charge is discretely distributed in some region of the space, then you can consider that dipole moment of that charge distribution discretely distributed can be given by this way: sigma I is equal to 1 to n. So, we do not have to utilize the integration, we can take work from summation. I is equal to 1 to n qi ri dash. Qi is the q1, q2, q3 etc. charges, and ri dash is the position vector of these charges with respect to some reference point. So, by taking the product of q1 r1 dash plus q2 r2 dash plus q3 plus r3 dash, vector sum of this will result a dipole moment of this discrete charge distribution. For a physical dipole, equal and opposite charges plus q and minus q, only we think about the two charges plus q and minus q in a some coordinate system x, y, z. We will see that figure. Then the position vector of the charge plus q is going to be r plus from the origin, and position vector of minus charge q is going to be minus r minus. So, substituting this, in this equation there are only two charge q1 r1 dash plus q2 r2 dash vector sum. So, qr plus minus qr minus, substituting because this charge is negative. So, substituting this one, magnitude of the charge we can take it outside. So, q into r plus minus r minus, that is equal to, this is displacement vector R1 minus R2, and that is equal to Q into D, where D is the vector from the negative charge to the positive charge. So dipole moment is a vector and its direction is always from negative charge to the positive charge. That is the direction of vector P, we remember. If this consistent with what we got in example 3.10, yes. If you put equation 3.101 into equation 3.99, you recover equation 3.90. So what was 3.99? P dot R upon R square. So R caret is the unit vector. So if you take an angle between these two vectors, that is going to be cos alpha. So P cos alpha upon R square. That means the same equation what we have got it in example 3.10. Notice, however, that this is only approximate potential of physical dipole. Evidently, there are higher multipole contribution. Of course, as you go further and further away, V dipole becomes better and better approximation, since the higher term dies off more rapidly with increasing R. So you can consider that this is the equations which represents, because of this charge distribution, the potential at a distance r because of the dipole term, and dipole term is dominant, but there is possibility that higher multipoles are also contributing potential at that distance r. But if we consider that r is very large compared to the distance d between the two charges, then in that case the higher multipoles, that means quadrupole, octupole, which contributes the potential proportional to 1 upon r cube, 1 upon r raised to 4, 1 upon r raised to 5, they are dying off more rapidly, and that contribution tends to 0, and the approximate potential becomes more exact potential because the dipole term is going to be more and more dominant, and it is going to be converted into the exact potential. So evidently, there are higher multipole contribution. Of course, as you go further and further away, V dipole becomes a better and better approximation, since the higher terms dies off more rapidly with increasing R. So if R is very large, all other multipoles which contributions tends to 0, and only dipole contribution is going to be dominant, and that is going to be more exact potential. Now, same kind of situation we can create at a near distance r also. How? If we consider that separation between the two charges, that is small d, is very small compared to that distance r. If we reduce that distance d with respect to r, even r is going to be the finite value. We are not changing the r. R is not too much large, but even if we shrink the two charges to very close to each other, then that is also going to be the same situation it can be created, and that is called a point dipole. Let us read this one. By the same token, at a fixed r, the dipole approximation improves as you shrink the separation d. To construct a perfect, which is known as a perfect dipole, or perfect or point dipole or pure dipole, whose potential is given exactly by the equation 3.99. What is that? 1 upon 4 pi epsilon 0 vector p dot r caret upon r square. You did have let d approaches 0. Unfortunately, you then lose the dipole term too, unless you simultaneously arrange for q to go to infinity. That means, what is the dipole moment? Dipole moment P is equal to q into d. D is the separation between the two charges. So if I am reducing the d and it tends to 0, the dipole moment is also going to be reducing simultaneously, because this is a product, and the dipole moment tends to 0. So this cannot be allowed. So what we have to do? If we reduce the separation between the two charges and we are converting a physical dipole into pure dipole or a perfect dipole, then simultaneously we have to increase the magnitude of the charge. That means the product q into d remains constant. So construct a perfect dipole whose potential is given exactly by the equation 3.99, you did have to let d approaches 0. Unfortunately, you then lose the dipole term too, unless you simultaneously arrange for q to go to the infinity. A physical dipole becomes a pure dipole. Then, in the rather artificial limit, d tends to 0, q tends to infinity. So, with the product, qd is equal to p held constant, and that means the dipole moment does not change. When someone uses the word dipole, you can't always tell whether they mean a physical dipole with a finite separation between the charges or an ideal point dipole. If what is the point dipole, now you understand. The separation between the two charges is very small compared to the distance d, compared to the distance r, so that d is very small compared to r, and hence the contribution of the dipole is going to be dominant. If in doubt, assume that d is small enough compared to r that you can satisfy the application 3.99. This figure represents that there are two charges, plus q charge, which is having a position vector r plus dash from the origin in this coordinate system. Another charge is going to be residing over here, minus q charge, and that position vector is r dash minus. Now, what is the separation between these two charges? This vector minus this vector. That is going to be the vector d from minus q to the plus q. This is the direction of the displacement vector. So, the magnitude of q into d is the dipole moment of this arrangement. You can see that. Dipole moments are vector and they add accordingly. If you have two dipoles, P1 and P2, and the total dipole moment is P1 plus P2. For instance, with the four charges at the corner of the square, as shown in a figure 3.30, the net dipole moment is going to be 0. You can see this by combining the charges in pair. Vertically, this arrow plus this arrow, the dipole moment is going to be 0, or horizontally, this arrow plus this arrow is equal to 0, or by adding up the four contribution individually using the equation 3.99. You can see that if I am making another configurations, that means if I am taking a square and on each vertices I am placing a charge like this. This is going to be minus q, this is going to be plus q. So, one dipole moment P1 is equal to, from this to this, q into d, this separation, and another dipole moment minus q is this side, plus q is this side. So, another dipole moment is in this direction. So, one dipole moment magnitude is same, q into d. Another dipole moment magnitude is going to be the same, but they are in opposite direction. So, the net dipole moment is going to be 0. You can take in a horizontal directions from here to here as well as here to here, or you can take a vertical dipole moment, that means from top to down, this dipole moment. Another one is from down to top, that means P2 in this direction. Again, both are going to be the same and they contribute 0. So, the net dipole moment of this configuration is going to be 0, but it forms a quadrupole, and that quadrupole moment is not going to be 0, and that can create a potential at a distance r. Remember, this is a quadrupole. As I indicated earlier, its potential is dominated by the quadrupole term in the multipole expansion. That means in the charge distribution, if there is a monopole terms is going to be 0 because the net charge is going to be 0. So, that is not creating any potential at a distance r. Dipole term is also going to be die off because the net dipole moment is going to be 0. So, that is also not contributing potential at a distance r, but this quadrupole is contributing potential at a distance r, and that is going to be dominant now once the monopole and dipole term is absent. Now, we will study about the electric field of a dipole. Until now, we have studied about the potential only. How to find out the electric field? Electric field can be find out from the potential. Very well equation. You know very well. E is equal to negative gradient of potential. E is equal to minus del phi. That means if the potential is differentiated with different coordinates, then you can find out the electric field components. Now, if we represent here, the V is a function of r and theta. That means we are taking r theta phi coordinate system. That means we are going to find out the ER, E theta and E phi, the component of electric field by taking a negative gradient of potential in spherical coordinate system. So far, we have worked with the potentials. Now, I would like to calculate the electric field of a perfect dipole. If we choose the coordinates so that P is at the origin and points in the z direction, then the potential at r theta in equation 3.99 is like this. So now we are going to consider this is going to be x, y, z coordinate system is there, and we are placing a dipole. Now we are representing a dipole moment as a vector, and it is aligned in the direction of z. So, and it is kept at the origin. So you can see that this is the dipole moment vector, dark one, and this is a distant point P, where which is having a position vector r. So I want to find out a potential at this point. So potential V is a function of r and theta. Theta is the angle subtended by this dipole moment vector with respect to the position vector of distant point P. So vector P dot vector r caret upon r square, that is multiplied by 1 upon 4 pi epsilon 0, that is the potential contributed because of this dipole. So if you want to convert in the spherical coordinate system, we take a projection from this point to in xy plane. So we'll get this point, and with respect to this point, if we make this line, that means this is going to be angle phi will be there. So you are having the three coordinates now, r, theta, and this will be phi. Phi is varying with respect to x 360 degree from 0 to 360 or 0 to 2 pi, you can see that. Theta is the angle with respect to z axis of this position vector r. So it can vary from theta is equal to 0 to pi, and r can have anywhere inside the space. So r can have minimum is going to be 0 and maximum is going to be infinity. That way we can say that we have represented the position vector r in 3 dimension, that is r, theta and phi coordinates. This formula makes explicit reference to particular coordinate system. Here it is spherical, and assume a particular orientation of P along Z. Now we are having a equation for the dipole moment in r theta, which is dependent upon r theta, and hence V dipole is equal to 1 upon 4 pi epsilon 0 r caret dot vector P upon r square. That means the magnitude of r is going, r caret is going to be 1. So P cos alpha or P cos theta upon r square we can write 1 upon 4 pi epsilon 0 P cos theta upon r square. Now we are interested to find out the component of the electric field. So ER is equal to, in spherical coordinate system, we have to differentiate potential with respect to r and negative gradient. So minus del V upon del r. So if you differentiate this expression with respect to r, that means P cos theta is going to be constant. This is going to be constant. 1 upon r square has to be differentiated, and differentiation of 1 upon r square is equal to minus 2 upon r cube. So minus 2, that means minus sign this and minus 2, that sign is going to be cancelled. That means 2p cos theta upon r cube, 4 pi epsilon 0 into r cube. So this is ER component we have obtained. Similarly, we want to obtain E theta component, minus 1 upon r del V upon del theta, that is equal to, again differentiation of now this one with respect to theta. So differentiation of cos theta is going to be minus sin theta. Substituting minus sign here with this minus sign, it is going to be positive now. So, and this r is going to be multiplied. So you can say that r into r square, that is going to be r cube. So P sin theta upon 4 pi epsilon 0 r cube, and this potential is independent of phi. So differentiation of this one with respect to phi is going to be 0. So E phi component is going to be 0. And thus, the electric field of a dipole moment, that is a function of r and theta, that is equal to, we are taking the summation of this, er plus vector e theta. So, common thing is this, P upon 4 pi epsilon 0 r cube, 2 cos theta, and unit vector in the direction of position vector r, plus sin theta and unit vector of e theta caret, or it is called unit vector of angular position theta. So, this way the electric field can be represented. Notice that the dipole field falls off as the inverse cube of 1 upon r. The monopole field 1 upon 4 pi epsilon 0 1 upon q upon r square into r caret goes as inverse square of cos. That means the electric field due to the monopole is proportional to 1 upon r square, and due to the dipole it is proportional to 1 upon r cube. Similarly, the electric field due to the quadrupole is proportional to 1 upon r raised to 4 and octupole 1 upon r raised to 5 and so on. This reflects the fact that monopole potential falls off like 1 upon r, dipole potential is proportional to 1 upon r square, quadrupole like 1 upon r cube and so on. The gradient introduces another factor of 1 upon r. That means potential due to the monopole is proportional to 1 upon r square, but electric field is proportional to 1 upon r square. Dipole potential is proportional to 1 upon r square, but its electric field is proportional to 1 upon r cube and so on. So you can see that the gradient has introduced 1 upon r. Figure 3.37a shows the field lines of a pure dipole. For a comparison, I have also sketched the field lines for a physical dipole in a figure 3.37b. Notice how similar two pictures becomes if you plot out a central regions up close. However, they are entirely different only for the points r. Thus, equation 3.101 represents a valid approximation to the field of the physical dipole. As I mentioned earlier, this regime can be reached either by going to a large distance r or by quizzing the charges very close to each other. So, this is a comparison of two types of the field. Field of a physical dipole. So, this is going to be positive charge, this is going to be negative charge. The field lines are initiated from the positive charge to the negative charge. You can see that. So, this is a non-uniform electric field because of purely a physical dipole, plus q and minus q, separated by distance d. But this is a pure dipole. You can say that separation between the positive charge and negative charge is very shrink. It is very, very small. That means d tends to 0 and q tends to infinity. That way the magnitude wise both are going to be the same. But this is a electric field due to the pure dipole. Now if you see that far field from both the dipoles are similar, but near field, that means near regions of this regime, that electric field is going to be different. So this you can convert into this field by shrinking this distance between these two, or you convert the physical dipole into the pure dipole and both the fields are going to be the same. Thank you very much, friends.